Welcome to lesson 27 of industrial automation and control. In this lecture, we will first look at pressure and flow control valves, something which spilled over from the last lecture. Then look at hydraulic cylinders, proportional valves and servo valves, and finally we will look at the structure of a full hydraulic actuation system. So, we look at the instruction objectives, describe the principles of operation of pressure and flow control valves and cylinders, basic components of proportional valves, learn about basic components of servo valves, and be familiar with the typical control architecture of hydraulic actuation systems. These are the instructional objectives of this lesson. So, coming over from the last lesson, pressure relief valves. These valves are typically mounted. So, you have these are not valves where these are connected in parallel in general, that is you have a pipe through which the main flow takes place, and this valve is going to be connected in parallel. Okay. So, in a hydraulic circuit, you will have the main line and you will have a pressure relief valve connected to typically to tank. So, this will be the valve symbol as shown, and there is an adjustable spring. So, the main power line through which the main fluid flows will be this. If the pressure at this point goes high, then this valve is supposed to operate. So, this point A is connected to the inlet A, and this point B is connected to the drain B. Okay. So, if the pressure goes high here, this is simply a poppet like thing, this one, which is loaded by this spring. This is a spring, you can see the cross section. So, the spring actually presses it down, the spring presses it down. So, when it presses it down, this is closed, but if the pressure at this point goes high, then this will be pushed up, and the fluid will flow through this to the drain, it will flow through this to the drain. So, that is the path, this path, this is the operation of the pressure relief valve. Now, sometimes you need to operate these relief valves in various modes using a pilot. That is, a pilot is a line from using which, by applying pressure from a remote place, you can operate a valve. So, there may be some normal operation mode of the valve, but you may sometimes the operator may like to override that mode and get into a different mode, and that he can do sitting in the control room while the valve may be at the field somewhere near the machine. So, here we have a pilot operated valve. See the operation. So, this is the pilot port, right. Suppose first of all we keep it closed. So, if we keep it closed, suppose it is sealed. So, normally fluid is flowing through this, going out through this, or rather opposite, it is going it's going through this, and because of this, it will actually, what happens is that the fluid is flowing through this tank and going out. Okay. Now, sorry, this is actually right, correct. So, this fluid is going through this like this is the inlet port and this is the outlet port, and there is you see that this is actually hollow, but so, and there is a slight hole here, slight capillary like opening, which is not shown. I am making it full. So, what happens is that the pressure here is generally in the steady state it is the same as the pressure here. So, on this pool the net force is 0. So, but there is a spring, this is a spring. So, the spring is pushing it down. So, this edge, these two edges, they are actually pressing against here and closing. So, there is no leakage to tank, directly the fluid is passing. This is the normal scenario. Now, suppose the pressure starts going high here. So, what will happen is that slowly, because of the capillary it will take some time, but the pressure here and pressure here after some time are maintained because of this opening. So, the pressure here will also go up. In this way, at some time the pressure here will go so high that it will push this poppet on this direction and there will be a leakage flow. This is actually a hollow. Can you see these dotted lines? This indicates that it is hollow and there is an opening. So, the fluid will start flowing through this hollow and it will flow out to the tank. So, the pressure cannot increase beyond a certain level. Now, suppose you want to at some points of time due to the operational requirements you want to open this valve. Before that, if you try to make it flow through this, it will not flow because it will close. So, there cannot be any tank to pump flow. On the other hand, if you now apply a pilot pressure here, if you apply a pilot pressure here, for example, you see you can apply pilot pressure using a directional valve. So, in this position of the valve, pump is connected to B. So, in this this is so in this position what is going to happen is that because you are applying pressure here, so you are pushing this, down. So, you are pushing this down. So, the pump will flow to tank. This will flow to tank. So, you can now by applying a certain amount of pressure, you can decide the level of pressure at which this will drain to tank. So, the relief level can be programmed. So, such things can be done using pilot operated relief valves. Going over to the next one, flow control valves. These are valves which are made such that the flow across them, irrespective of the pressure variation, at the inlet, the flow through the outlet is going to be constant, and this can be adjusted by this. I mean, there can be different settings of flow and one can adjust that setting. So, how is that achieved? This is achieved basically by the fact that this is the inlet port. So, what is the fluid path? The fluid path is through this, like this. This is the fluid path. Okay. So, there are two obstructions. One obstruction is this one. This is actually a cross sectional view. So, the actual thing is like this. It's a cylinder with a notch, with a V shaped notch in the middle. So, you can see that the amount of, because the notch is V shaped. So, if this is rotated, then the ends of the V will come here, it will become like this crescent will become like this. Then the fluid has to flow through this much of opening. Right now it is flowing through this much of, so actually because the cross section varies, here the cross section is low, here the cross section is more, here the cross section is maximum. So, as you rotate it, this cross sectional area through which this flows can be determined. This is the first thing. So, the flow setting can be adjusted by moving this valve, moving this notch. Now, what happens is that suppose the pressure here goes up. If it goes up, then because it is flowing at a certain across a particular notch, there is a particular pressure drop at a particular flow. So, this pressure will immediately tend to rise here. Now, if the when the pressure rises, this will apply a force. If this applies a force, then no, actually what will happen is that if the pressure rises here, then first the pressure will rise here. Now, this means that this pressure will act, the pressure will also, so the flow will tend to, because of that the flow will tend to increase here, but because the pressure rises here, so the flow will, this pressure will pressurize it here and here, so that this spool will move this side. Now, if this spool moves this side, you can understand that this opening will close. Once this opening closes, then there is going to be a greater pressure drop here, and naturally since this pressure drop is fixed, it has gone up, but at this level it is fixed, then if you increase the pressure drop here, then the pressure here will fall. So, in this way the pressure is going to be adjusted, there is going to be, this will stay, a particular flow will take place when the pressure difference between these two, what is the pressure difference between these two, why is this in equilibrium? Because there is an upward pressure here, there is a downward pressure here, and there is a spring force which is downward. So, it will, so the difference between this pressure and this pressure in any steady state is always going to be equal to the spring. Therefore, the spring sets the pressure difference across the throttle. So, it is set by the spring, it will always be equal to the spring force. And so now, so what is going to happen is that at a particular opening of the V notch, if you have the pressure difference fixed and if you have the opening cross section fixed, then the flow is going to be fixed. So, this is the way that, so the moment the pressure goes up, this spool will adjust and control the pressure here such that the flow to the load is going to remain the same. So, this is the principle of flow control valves. Now, we look at, so finally, so now we have studied a number of valves, right. So, we have first studied pumps and motors which deliver the fluid and finally use the fluid, motor is a rotary actuator. Then we have seen how the fluid can be, its directions can be changed, and on its path how flow and pressure can be controlled. So, now finally that fluid will go to an actuator. So, one of the actuators can be a rotary actuator, is motor, which we have already studied. Now, we are going to see a linear actuator, which is a cylinder. So, cylinders are generally of two types, one type is called single acting, the other type is called double acting. So, single acting means that it by force it moves only in one direction, then it generally comes back either by gravity or by spring force, etc. While double acting means that by force it can be moved in both directions. So, for single acting generally the return stroke is not loaded, while the forward stroke is loaded, while for double acting both strokes can be loaded. It is very simple, single acting cylinder, this is a single acting cylinder. So, if you put some pressure from the pump, it will go up, it will create a force and it will go up. So, that is the power stroke going up. On the other hand, if you connect it to tank, in this case it is by gravity. So, because of the load this thing will come up and the fluid will be pushed out to the tank. So, if you want to have the power stroke, you have to connect it to pump, if you want to have the retraction stroke, you have to connect it to tank. For double acting cylinders are also very simple devices. So, here you can see that you have two ports, one is pump, one other is tank. Actually, you have two ports. So, so if you connect this one to pump and this one to tank, then the fluid will enter here and will go out here and will be pushed in this direction, On the other hand, if you reverse that, if you take this one to pump and this one to tank, then fluid will enter here and will go out through this direction. Only one thing to note is that for the pressure that will be required to move this, that is the we want to mention that this cross sectional areas are different on the two sides. If you have, this is called a single rod, that is the rod to which the load is connected only on one side. So, therefore, this area is going to be less than this area, A1 and A2. So, A2 is greater than A1. If you have a double rod cylinder where you have a rod on this side also, then it may be that A2 is equal to A1, or even A2 can be less than A1. So, this is a very simple device. Now, so far we have mostly seen, apart from pressure control and flow control, we have mostly seen valves where the direction of the fluid is changed. So, we have seen mainly directional valves. Now, we are going to look at some valves where the flow or pressure can be controlled in a continuous or a stepless manner. Okay. So, it is, so therefore, we use what are known as proportional and servo valves. So, you have here what the the advantages are that you have a stepless control of position, force, velocity, etc., and you can drive these are typically electrohydraulic valves. So, that you can drive them accurately mainly using current, and so that you can sometimes have computing interfaces. One of the major areas of application is avionics. So, the onboard flight computer will drive these actuators such that the plane can fly. So, obviously, you use hydraulics for high power weight ratio. Sometimes you can improve the power weight ratio and drive very high loads using multiple stages of hydraulics, and they use open, partially open or partially closed, and sometimes full closed loop control. So, these are generally very precise devices, quite expensive, difficult to manufacture, and mainly used for precision motion of very high power loads. So, we will start with proportional valves. So, we can have open loop technology where when can you use open loop control? You can use open loop control when this we have studied in control theory, that why do you need feedback? You need feedback when you know that the system model can change and there are lots of unknown disturbances. So, if you have this sort of situations, then you use closed loop feedback control, but for closed loop feedback control you may need an expensive feedback arrangement. So, if you can sometimes do away with that, if you know that your system is highly stable, does not change, there is little uncertainty, very well characterized, and you know the load. So, there is not going to be an unexpected kind of load. In such a situation, you can use open loop control, and typically in a control system there may be multiple loops. So, if you have some of the loops closed and maybe the final, these are generally used for creating motion. So, maybe if the final motion of the final element is not sensed, then I call it a partial closed loop control. So, proportional valves use this open or partial closed loop control, and they are very highly characterized devices. So, basic idea is to create flow or pressure proportional to spool stroke. So, basically there is it is like a directional valve only. Only thing is that in directional valves, when you switch on one side of the solenoid, it comes and sticks at one end. When you energize the other side of the solenoid, it comes and sticks at the other end. Here you are not going to do that. Here you are going to make continuous motion of the spool, and so all these openings are going to open to various extents, and thereby you are going to control the flow or the pressure. So, you are so basically the structure is the same. So, by it creates flow or pressure proportional to spool stroke. So, it is so the flow or pressure will be proportional to the motion of the spool, and this will in turn create proportional force or speed at the actuator depending on what the actuator is. Let us consider a linear actuator at this point of time, and as we have seen that in the, as we said that in the pilot operated relief valve you can control the pressure at which the valve will vent. So, how do you do that? You do that by controlling the pilot pressure. How do you control the pilot pressure? You can put a proportional valve at the from the pump and then connect the outlet of that pump of that valve to the pilot port of the relief valve, and then by using computer or using using manual operation you can control the relief pressure. A typical proportional valve will have these elements. So, it is operated by a control voltage which can be given manually or which can come from a computer. Then there is usually a set of electronic circuits which do various kinds of things, which do filtering, which will do amplification, which can do, sometimes if part of it is digital they will do digital to analog conversion, and there is a main thing is that it must add some power, that is there will be a servo amplifier and there will be a voltage to current converter. So, finally, from this control voltage which does not have any power you are going to drive some current. This current will be applied to a proportional solenoid. So, the characteristic of the proportional solenoid is such that at a particular current it can create a particular force. So, if it can create a particular force or it can create a particular stroke, as we shall see that proportional valves can be either force controlled or stroke controlled. So, if you control the stroke, then the this is the coil part of it, that is why these are called electrohydraulic. So, this part is electrical. This is the hydraulics. So, if you create a force or stroke on the spool you will get a corresponding flow or pressure, and that flow or pressure can be applied to the this is the actuator finally, which is connected to the actual load which you want to move machine. So, this is the cylinder or the motor. So, these are the typical structure of a proportional valve. So, proportional solenoids are typically made, if you want to have a force controlled proportional solenoid, proportional valve, then what you do is that you do actually, how do you do force control? You do current control, and you do current control, and then you have made the solenoid such that this is force stroke characteristic. So, you see that for a good range of the stroke the force remains constant at a given current. So, by changing the current you can take the force up and it will stay constant over a length of the stroke. In fact, it should be mentioned that these valves, the stroke length is actually very small, it is of the order of millimeters, full stroke length. So, therefore, generally the stroke length is not large, and therefore, the valve is actually expected to operate only in this zone. So, you have a constant current to force ratio. So, therefore, if you want to control the force, it is equivalent to control the current, which is very simple, as we will see later also that current feedback is very much preferred, because it is very easy to get that feedback. For example, a typical very cheap Hall effect sensor can give you a very good current feedback. Sometimes a current sensing resistant, you can drive the current through a small resistance and then take the voltage drop, that will give you very good current value. So, that brings down the cost if you really wanted to. On the other hand, remember that this force control strategy is essentially dependent on this force current characteristics of this valve. So, that must be ensured, and if it is not good enough, then your force is not going to stay constant. On the other hand, if you have where you have stroke control, oh, we have not drawn the stroke control. Let me just go ahead and actually I, on the other hand, yeah, okay. So, go back. Okay. So, you see that this is a, I am sorry, yeah. So, typical construction of a force controlled proportional valve. So, what you are happening is that you see here you are giving the electrical connection, that is the servo amplifier current has to be driven here, that will this is the torque, so called torque motor. So, what will happen is that it will, this is the connector. So, if you drive the current, then what will happen is that, say, this will move, this magnet system will pull it and it will tilt slightly. So, it will push it, here. Once it pushes, this is actually connected, this is actually connected. So, once this pushes, this valve will shift, this is the spool, you can see the spool, this is the spool shaft. So, once this moves this side, this is the pump which gets connected to this port, and this is that, this port gets connected to the tank. Okay. On the other hand, if you move it this way, then this will get connected to this port and this will get connected to this port. So, this will make the spool shift. In this case, because of this feedback, it will move a certain only a certain distance. In the case of, so you see that in the case of force control, in the case of stroke control solenoids, you actually put a position transducer. So, you actually put a position transducer and see the stroke, and you give feedback. In that case, you can see that this characteristic of the, because it is a feedback system. So, therefore, the characteristic of the valve need not be very closely controlled, but the position transducer accuracy is very important, and the characteristic of the overall proportional solenoid is going to be still going to be fairly constant. Okay. So, now, so this is a this is a typical application circuit. What we are trying to do is, this is a single acting cylinder. So, you can see that if it is in this position, then the cylinder is locked. You can see that this is a cylinder. So, the cylinder is locked. Why the cylinder is locked? The cylinder is locked because of this relief valve. See, this is a check valve. So, flow cannot take place from this place to this place. If flow has to take place through this path, then a certain pressure difference is required. So, unless the weight, so the cylinder cannot come back by its own weight, because the fluid cannot go out of this chamber. So, if you put it in the central position of this 4-way valve, 3-position 4-way valve, then the cylinder is locked and it does not slowly come down because of its own weight. On the other hand, if you connect it to this position, this means that these symbols mean that these are proportional directional valves. So, it is not only that the position of the valve can be shifted to one of the three, as is commonly known in directional valves. The flow rate can also be changed by using proportional control. So, the rest is simple. If you connect it this place, the fluid will flow into this and will flow through the valve. On the other hand, if you connect it to this position, then the fluid will flow through this, through the check valve, and go to this and come back to the tank. So, this is, so you see that here you, by using this proportional directional valve, using only one element, you are able to not only control the direction, but also control the velocity or the speed by using the proportional valve. That is sometimes an advantage.